Double wound solenoid. In this example, we simulate a special kind of solenoid. It is designed to feature a low value of inductance. It is more a resistor than the inductance. I am going to apply DC voltage, and my task is to measure the current versus time dependency. Also, I will calculate the resistance, the inductance, and the temperature rise. So here I am going to simulate two problems. Magnetic problem to calculate the current, and transient heat transfer problem to calculate the temperature. Okay, let's start QuickField now. In QuickField, I create new problem. Coil. Next. Problem type is transient magnetics. Coil features rotational symmetry, so the model class is axisymmetrical and units are millimeters. And I will need a circuit file to specify the connection scheme, so I type in the circuit file name here. Circuit 1. Next. Here I should specify the integration time and the time step. I have already simulated a similar problem, and I knew that the switching process would finish within 100 microseconds. And I can utilize automatic time step. Finish. On the left you can see the problem pane, and on the right is the geometry model editor window. In axisymmetric problems, the axis of rotation is a horizontal one. So here first I insert a rectangle, which would represent the carport core. The rectangle width is 20 millimeters and height is 10 millimeters. And I insert another rectangle with a height of 8 millimeters. Close them to fit. Now this is the cardboard core. Next I'm going to insert a circle with a diameter of 0.4 millimeters, and the insert point would be here, 5 millimeters above the axis. And I need 5 more copies to the right. So switch to select mode, select, edit, duplicate selection displacement by 0.6 millimeters, and I need 5 copies more. And I need 6 turns to the left. Right click, duplicate selection, minus 0.6 millimeters, 6 more copies. All in all, I have 12 turns. Apart from the core and conductors, there is an air. You cannot include in the model the infinitely large area. I should limit the simulation domain, so switch to insert mode, draw the line along the horizontal axis, change the line type to the half arc, draw the half arc, switch to select mode, select and remove all objects located below the axis. Use them to fit. Now let's assign labels. Through labels we can distinguish objects and provide material properties. Switch to select objects mode, click the object to select and type in the label name here. This is air and this is air. Let's zoom in. Select objects, click, this is core, and these are positive current conductors. To select multiple objects at the same time, hold the control button pressed. I plus, and these are negative current conductors. I minus. And far away from the core, the magnetic field fades to 0, so at this boundary I should also assign label far away. And for this label, I will specify zero magnetic potential. Now, to provide material properties for the label, double-click the label name in the tree. Magnetic permeability of the air is 1. Magnetic permeability of the cardboard core is 1. 0 electrical conductivity. Coil is made of copper with permeability of 1, conductivity of 56 megasiemens per meter, and conductors are connected in series. And the same is true for I-, 56 times 10 to the power of 6 siemens per meter, conductor connected in series, and the field source we should specify in the electric circuit. Open the electric circuit, yes, and here put all the conducting blocks, I- and I+, and here I put the voltage source, and I connect the voltage source to the winding with the wire. The voltage source magnitude is 0.1 volts DC voltage. And remember, this is the double solenoid, so this conductor has opposite direction. Everything is ready. I should build the finite element mesh in the geometry model. Just press this button and the mesh will be generated. Save all problem files and solve the problem. The problem is solved. Let's take a look at the results. Here you can see the magnetic field lines at the moment of 100 microseconds. Let's zoom in. I can use the contour tool, click to select the conductor and calculate the current. I can see how the current changed in time. Open the electric circuit. Here you can see the current changed in time. And if I divide the voltage by the current value, I will get the resistance. The voltage value is this, and the current value is this. So the resistance 0.058 ohms. Now, what about the inductance? I can calculate inductance using the stored magnetic field energy. The inductance is the ratio of the stored energy, doubled value, divided by the current value squared. So let's calculate the energy. To calculate the energy, I should select all objects. Again, I will use the contour tool and select, just click the edges, follow to the integrals. Here is magnetic field energy. Copy this value, paste it here, energy, and the inductance is double this value divided by the current squared. This is the inductance is in Henry. Remember, this is a specially designed solenoid with double winding featuring low inductance. What would be inductance with ordinary winding? We can easily calculate it. Just rotate this block, solve the problem again, open the results. You see the field configuration has changed. Let's check the circuit. Now the current raise time is much slower. Anyway, the current value should be the same. We may need more time to reach the steady state condition. Let's modify the problem properties, timing, 200 microseconds. Solve the problem again. Half a minute and you will get the results. Open the circuit. Check the current value. 1.714. 1.714, exactly as it was. Because the resistance is the same, but what about the inductance? Let's measure the magnetic field energy. Again, I use the contour tool to select all the objects, follow to the integrals, and calculate the energy. This is the value. Copy it here. The new value of inductance will be double this value divided by the current squared. Anyway, now you see in the double wound solenoid the inductance was this value, and now in normal solenoid the inductance is this value, and the ratio of inductances is 18. Okay. You see we have other integrals here, and you can see the Joule heat integral here, which should be equal to the resistance multiplied by the current squared. Let's calculate resistance multiplied by the current value squared. This is the Joule heat power in watts. 0.1714. Exactly the same. So we know the Joule heat power. What will be the temperature? To calculate the temperature, I need to simulate heat transfer problem. Let's do it. I create new problem in QuickField. Coil heat. Next, problem type transient heat transfer. Again, I would like to calculate the temperaturized dynamics. Model class is axisymmetric. Let's need some millimeters. To be able to automatically pass Joule heat distribution from magnetic problem into the thermal problem, both problems should be based on the same geometry model file. The geometry model file here was coil.mod. So here I click Browse and look for the coil.mod. Here it is. Next, again in transient problem I should specify integration time and time step. In fact, the thermal process is much slower than the magnetic process, so I will simulate 5 minutes 300 seconds with a time step of 5 seconds, and the initial temperature is 20 degrees Celsius. Finish. The geometry model is the same, but now for the labels I should provide thermal properties. I'm not going to calculate the temperature distribution in the air, so I do not specify any properties here, just click OK. For the core, which is made of cardboard, thermal conductivity is 0.05, density is 900, and the specific heat is 2000. Okay. For the coil, which is made of copper, thermal conductivity is 380, density is 7800, and the specific heat is 413. And the same for the other label, 7800, 430. You see, I do not specify the loss value here, because I'm going to import the losses from the magnetic problem. So to be able to import losses, I need to put the link. Open the problem properties, follow to the links, generated heat, browse, and look for the coil.pbm. Coil PBM. Magnetic problem. Open, add the link. OK. I do not specify the temperature distribution in the air, but I should specify the convection condition on the coil surface. So I need to assign a label here. Actually, all these faces are cooled by the air. So for the edges, I assign label convection. And for this label, I specify the convection coefficient, which is 5, and the air temperature is 20. And this label I do not need here, so I do not provide any properties for this label. Just click OK, and you see the 0 mark next to the label name. That means that this is not an unknown label. This is a label that holds no data. It doesn't affect the results. So we have thermal problem ready. We have provided material properties. We have specified the link. Let's solve this problem. And we've got the message: the linked problem results are out of date. Well, indeed, you see both problems share the same geometry model file. And here I have modified the geometry. I have assigned label convection. I have provided properties for this label here in transient heat transfer problem, but I should also provide properties for this label in magnetic problem. In fact, this boundary has no physical meaning in magnetic problem, so again, for this label I do not provide any properties. Just click OK, and again you see the 0 mark. So this label doesn't affect the results. Anyway, the geometry model has been modified, so I need to run the analysis again and solve magnetic problem. You see, model was modified. Let's take a look at the results and make sure that the results are the same. I open the electric circuit and check the current value. It should be 1.71. Yes, the results are the same. Now solve the thermal problem. Let's take a look at the results. And here you can see the temperature distribution after 300 seconds of heating. You can change the time. That was after 30 seconds. That was the initial temperature distribution plus 20 degrees. And again, you can right-click any point and take a look at the time plot to see how the temperature changed in time. You see, the temperature is not yet stabilized, so you might need to change the simulation time and run the analysis again. So this way, in QuickField, you can simulate different configurations of solenoid and calculate the temperature, the inductance, the resistance of the solenoid. Now we almost reached the steady-state condition. If you search for the double wound solenoid on our website, you will find the example page. Here you can read about problem setup, browse the solution section, take a look at the result pictures, and download the simulation files. Simulation files may be opened and the results may be viewed using any QuickField edition, including QuickField Student Edition, that you can download from our website for free.